Hi everyone. This is going to be the presentation of our work that is entitled An Application of Model Reference Adaptive Control for Multi-Agent Synchronization in Drone Networks. The work is going to be presented by me, Miguel Felipe Arevalo, and I'm going to share the presentation with Yejin from University of Houston. So the outline that we're going to discuss today is going to be basically a brief introduction of the application that we are using, the description of the model that we are using for the experiments that we done, and the parameterization of like a leader follower configuration that we are using through the experiment. With that, we discussed the controller design for the leader and the followers in the configuration that we're proposing, and at the end we present like a set of experiments that we develop. And with that, we can highlight like some conclusion and future research of this work. So as a brief introduction, like the main topic that we are considering in this case is a multi-agent system configuration. So the idea with this type of application is that we are having a network of a set of agents that have like a common behavior or like a common goal. And the idea is like through some communications, we can guarantee or accomplish that goal. So we can see different type of application of this theory that can be like the use of automatic bait calls, the use of drone for like different applications, or even in terms of analysis, like the use of social networks, social media nowadays, to have like some focus information in a specific field. So with that in mind, like the specific problem formulation that we are considering in this case is that we are considering a network of any intercommunicated drones. Each drone have some wireless communication. So the idea is that it can share like some information with its peers. And with the information that we are sharing, the idea is like we are defining some synchronization error that basically is like the information of the states that we obtain through some dynamical model. And with that information, the idea of the synchronization error is that the difference between the states of one drone and another drone is going to tend to zero. Just like for some highlight of the notation, we are using M as the notation for the leader. And the graph that we are using in this case is the drone that we can see, and the drones that we are using through the experiments.
So I'm going to introduce our drone system very shortly for experiment. The system is composed with hardware and software. The hardware includes our real drone called MTX, flight control unit, and flight control computer. And software includes the open source firmware, its MATLAB API, motion capture system, and ground control station. So the process is like once we send the MATLAB API, the ground control station sends the command to real drone, and at the same time, the motion capture system detects our drone's information. Then the all obtained information is interchangeable between the drones through ground control station and motion capture system using Wi-Fi. And in the next slide, we have simple details of quad rotor's mathematical model in terms of its attitude dynamics, and its kinematic equation for Euler's angles are expressed in this slide. And in the next slide, we have quad rotor's mathematical model in terms of its translation dynamics. In this paper, we talk about only the vertical axis, so the translation dynamics are narrowed down to the vertical model. And here is a linearized model by taking Laplace transform. And in the next slide, we are going over the procedures to get the vertical dynamics model, which is GVZ in this linearized model. And as for the system identification, so first we do the experiment to obtain data by injecting pseudo-random binary sequence. The left figure shows the input, the first along the z-axis, the output, the vertical velocity, and the generated PRBS input signal. The obtained data is pre-processed to remove any bias and time delay. Then this pre-processed identification data set is used to identify the system through an optimized predictor-based subspace identification method, which predicts the state sequence with past and future window parameters. At the last of this technique, we can estimate the modal order using singular value decomposition, and our vertical velocity system is estimated as a second-order system because usually the drop is noticeable when valuable information is contained in the data set. So in the next slide, we have the obtained state space matrices and the transfer function of the vertical velocity model, which was applied to the test, the classical PID controller. And in the next slide, we are going over the PID controller. design. So firstly, the model order has been reduced for simplicity to design the PID controller through a loop shaping method with the open loop transfer function. GVZ reduction is the reduced vertical velocity model, and L reduction is the open loop transfer function, and RI is the PID controller, which was designed using some calculated parameters, including mu and other L's under loop shaping requirements. And final PID gains were computed using the three equations in this slide. So next slide, the Felipe will talk about the MREC controller.
Yeah. So with the information of the the leader follower configurations that we're proposing, we considering given the effectiveness of the PID controller as the controller for the leader configuration. Yeah. For the followers, we define a model reference adaptive control that is gonna be used using the communications that all the drones in this case can have. So basically, for the formulation of the model reference adaptive control, we define some assumptions to guarantee that there is going to be a synchronization in terms of the dynamics and the input that are considering in a state space representation of a common linear model. Yeah, so in this particular case, we considering two sets of matching conditions, where it's considering as feedback matching conditions and complete matching condition. The feedback matching conditions guarantees to synchronize the dynamic of an agent with respect to the reference agents, and the complete matching conditions guarantee the synchronization of an agent with respect to the peers of an agent in a neighborhood. So with that in mind, with the information of the leader, we consider in two cases. We consider in a case when we have a follower drone that have direct communication with the leader, that in this case is the PAD based like drone that we already developed. So with that in mind, we developed a set of adaptive gains that basically are composed of some like adaptive parameters and the difference of the states that we are communication using this matrix P that basically is obtained through some linear Lyapunov mathematical equation and information of the linear representation of the system. So we're considering this case of follower that have like access to the leader or the reference drone, and we're considering a second scenario of drones that doesn't have like communication with the reference. So in this case, the information needs to be communicated to the neighborhood, and the objective is to accomplish the synchronizations even when we don't have like the information of the reference drone. So this is a brief extension of the previous case that I presented, but in this particular case, the set of adaptive gains that we are using, considering just the information that we can uh, share with the drones that are in the neighborhood of an agent. So with that in mind, we defined a proposition that is based on some theory that was worked a couple of years ago. So with that in mind, we defined a set of agents with the assumptions that we are considering. And we need to guarantee that there exists like a follower drone that have like the dynamics that we obtain through the linearization method. That even if it's not connected with the reference drones, we can guarantee that there is going to be a synchronization. For the theorem that we are generated, the validation or the mathematical proof is done using some Lyapunov theory. So we're defining the Lyapunov function, and the idea is to validate that is valid and accomplish of all the Lyapunov like parameters to guarantee that the synchronization error tends to zero. With that in mind, we can start like the set of experiments, and Yejin is going to start to explain them.
Yeah, so in this paper, we conducted 5 experiments to verify the communication stability of the MREC controller and compare both controllers' performances in terms of robustness with or without some weights and energy consumption. The first experiment was done by injecting double lead signal to show each controller's performance in this slide. In both figures, the blue line is the reference signal and the red line is the output signal. We observe that MREC controller shows slightly more sluggish response and higher overshoot than PID controller, but we assume that it's because of more computational complexity in MREC controller. And we are going over the second experiment. So both controllers were tested by gradually adding weights from 20 to 100 grams with the same injector reference signal to verify the robustness of both controllers. And in this experiment, we observe that even though the PID controller has less overshoot, both controllers' performance in terms of its robustness and adaptability is comparable. And in the next slide, we are going over the third experiment. So in the third experiment, the power consumption of both controllers was verified by injecting the same reference signal until either the PID or MREC controller failed. In the figure on the right, PID controller, which is blue line, has been failed earlier than MREC controller, which is red line. This observation has been validated through voltage consumption. In the voltage plot, the PID has much more fluctuations than MREC controller, and theoretically, the voltage fluctuations cause more energy consumption and or device malfunction. So we can conclude that PID controller has higher power consumption than MREC controller in the same experiment, and this caused earlier failure than MREC controller. And in the next slide.
So far with the experiments that we have done at this point, we were just considering like independently experiments of the PID or the MRAC and validated with like different change in the parameters of the model that we were considering. So now for the last two experiments, we include the wireless communications to configure graph configurations in the set of agents that we have in the laboratory. So in this particular case, in the graph that you can see, we defined a reference that is denoted by the blue line. We have like the leader that is denoted with yellow with the configuration of the PID controller that we previously defined. And these leaders send information to a follower that doesn't have access to the reference. And it's gonna try to accomplish the synchronization with the information that is obtained from the leader. So with the red line in the graph, we denote the follower that include the model reference adaptive control that we have, and we can guarantee a synchronization of the states in the network that we are proposing. Yeah, it is important to highlight that there is like a delay in the information derived of the wireless communications that we have in the network. With that, the final experiments that we propose, it was considering the whole network that we have available in the laboratory. So we have a 3-drone configuration network like a scenario. So we define as well a reference signal that is denoted by blue. And we have the leader drone that is the one that have access to this reference signal and is the one that is working with the PID controller. And these leader drones send information to the followers drones that in that particular cases are the yellow and the purple line. We can accomplish again a synchronization considering as well the delay in the wireless communications that we have. I'm going to present to you like some video of the experiment in this particular case. So the experiments you can see in the middle is the leader drones, and the behavior that it's given through the reference signal, it's synchronizing with the right and left drones that we can see in the laboratory. Yeah, so with that in mind, we conclude and guarantee that we can accomplish a synchronization using a model reference adaptive setup in a network. So as a conclusion, this study proposed an experimental framework from a distributed model reference adaptive control in a multi-agent synchronization scenario. This adaptability proves like robust performance in the face of uncertainties or discrepancies in the physical parameters of individual drones that can be found in like different type of applications in real life. So with that in mind, some future research should be focused on incorporate like some robust parameters, even in the controllers that we are using, not just guarantee that it's robust by itself, or maybe we can explore like different scenarios with graph that change over the time, or with agents that lose the communication in some points, just to make some robustness of these type of applications. With that, there is the contact information of us in the slide, and we conclude. We thanks for the time. Okay.
Okay. Thank you very much.
Thank you.